The sound is it?
Hello,
Yes, sir.
you can hear me clearly?
Yeah.
Should I share and check?
Yeah, please. Yes, sir. Visible.
Okay. And can you see the
Uh,
slides moving?
yes, yes, sir. Yeah, slides are changing, sir. We'll start exactly at 10 o'clock, sir.
Okay. My
Okay.
voice is clear, no? Okay.
Yeah, it's perfect, sir.
All
Thank you.
right. I'll just be back.
Okay, sir.
Magic man.
Hello, Viswanath sir.
Yes, can you hear me?
Shall we start, sir?
Yeah, can start.
So, good morning, everyone. It's our pleasure to welcome Dr. Viswanath, a renowned scientist at Philips with over 10 years of experience in medical image computing. Viswanath has made a significant contribution to the field. He holds a doctorate from IIT Bombay and Monash University, Australia, and his thesis on enhancing simultaneous PET MR imaging earned him the IITB Institute Best Thesis Award. Vishwanath has 7 years of industry experience working on medical image computing problems across various modalities. He has published numerous papers in prestigious venues like medical image analysis, neuroimage, MICCAI, and ISBI. We are honored to have Vishwanath with us today. His expertise and insight will undoubtedly enrich our understanding of medical image computing. Please join us in extending a warm welcome to Vishwanath sir. The session is over to you, sir.
Thank you. Let me hope my screen is visible
Yes, sir, it's visible.
and my audio is also clear.
Yes, sir. Yes, sir.
Okay. So hello to everyone, and thanks for the invitation and the kind introduction. I will share a few aspects about newer trends in AI-based image processing, specifically to applications in medical image computing. And I also plan to show how AI-based image processing is being used currently at Philips in the MR unit where I work. Just a bit of background, all of us are witnessing, and it is undeniable that machine learning is revolutionizing our healthcare system, enhancing nearly every aspect with the power of data science. Right? Take the example of electronic health records. Natural language processing, for example, has made documentation faster, easier, and this has allowed healthcare providers to spend more time on patient care. At the same time, predictive analytics provide early warnings of, for conditions like sepsis or heart disease, and this can potentially save lives due to early detection. On the other hand, if you go to robotic assisted surgery, innovative systems like the Da Vinci surgical system, they harness machine learning to boost surgical accuracy, reduce errors, and improve patient outcomes. This is changing the landscape of minimally invasive surgeries. Third, personalized medicine. Machine learning analyzes genetic and lifestyle data, is crunching a lot of data that comes from various modalities to determine the most effective treatments with the fewest side effects. This means that healthcare can be tailored to meet each patient's unique needs, personalized medicine. Fourth, accelerating drug discovery via machine learning is it's accelerating the identification of drug candidates by predicting how different molecules will interact with each other. This drastically reduces the time and cost involved in bringing new medications to market. Lastly, we are well aware of AI in radiology. AI in radiology manages vast amount of images data to ease the workload of radiologists. It allows for precise tumor grading, for example, submillimeter segmentation, and anomaly detection. And these all put together enhance clinical decision making and efficiency. Here are some additional examples. These are illustrating the immense impact of data science and machine learning in electronic health records. For example, organizing multiple reports into a single document that can streamline insurance claims processing, etc. Analyzing organized data across different regions can also help identify the role of demographics and genetics in the progression of health in a given locality. For robot-assisted interventions, you could also think of, robots can create surgery videos for resident doctors, not only participating in the actual procedure, but also summarizing them using augmented reality or virtual reality for a rich educational experience. And we have already discussed the significant advancements in personalized medicine, drug discovery, and AI in radiology. So, is there a gap in AI adoption in medical imaging? So, while AI and machine learning have made significant strides, there are several areas where these technologies still have a long way to go, such as in analyzing data from various different modalities, including images, textual data, uh, uh, you know, cognitive tests, and so on. So if we take the example of neurodegenerative diseases, consider diseases like Alzheimer's, amyotrophic lateral sclerosis or ALS, and Parkinson's. Despite so many advancements, we still do not fully understand the pathophysiology of these diseases. We lack the clarity on who is at risk and how these diseases progress from cellular changes to physical symptoms. Uh, 50, 60 years ago, our main source of information came only from postmortem studies, revealing reductions in hippocampal volume and increased ventricular volume. This was known to be one of the biomarkers for Alzheimer's patients. But today, non-invasive imaging modalities offer more insights into cellular and metabolic changes, but we still do not know the fundamental causes. Crucially, we also lack mechanisms for early detection, which would allow for better disease management. Despite having organized data from genomics, proteomics, brain imaging, and clinical records, the challenge still remains. So while the journey of AI and ML in healthcare is highly promising, some challenges still need to be overcome, showcasing the limitless potential yet to be realized. One example of current state of detecting
ಮಲ್ಲಿ
sorry.
ಆಮೇಲೆ ಇಸ್ಕೊಂಡು ಅದೇ ಕಟ್ ಮಾಡ್ಕೊಂಬಂದ್ಬಿಡ್ಬೇಕು.
So one example of current state of detecting neurodegenerative disease is quite telling. If you look at the picture on the left, by the time we can observe cognitive impairment, it is almost at a point of no return. That is, dementia patients, by the time they are able to show cognitive impairment, it is almost at a point of no return. Structural MRI is slightly better, as it can detect stages of mild to low cognitive impairment. Interestingly, certain protein lumps specific to neurodegeneration, like amyloid and tau proteins, can be detected using molecular imaging techniques, such as positron emission tomography scans with specific radio traces. Even more sensitive are the uh, uh, blood samples or fluid samples taken from the cerebrospinal fluid, which can be identified using a biopsy-like procedure near the spine. So in principle, it is possible to detect these neurodegenerative diseases at a very early stage, enabling us to potentially alter their progression. However, the main challenge lies in the invasive nature of these procedures. The CSF extraction involves a painful procedure which lasts about 30 to 45 minutes, where a needle is inserted into the spine, in the back. And talk about positron emission tomography, these scans involve ionizing radiations which could harm otherwise healthy patients. The figure on the right provides another perspective on how neurodegeneration progresses in terms of detectability across different modalities and its manifestation, physically as well as chemically. So while the journey of AI ML in healthcare shows incredible promise, these kind of challenges to crunch images and data coming from different modalities is yet to be fully realized. Today, we'll look into some aspects related to ML specific to medical imaging. Medical imaging, as you know, it has energy sources coming across the electromagnetic spectrum as well as longitudinal imaging. So when these waves, be it electromagnetic waves or longitudinal waves, when these waves interact with our tissues, our tissue reacts in a specific way, and the art of measuring these reactions to certain waves that hit us gives rise to different imaging modalities. For instance, shining a focus beam of near infrared laser onto our skin generates interference patterns, which gets reflected from different blood particles revealing certain disease types. Similarly, X-rays passing through the body, they get attenuated, energy gets lost, and based on the tissue type, the X-ray loses energy. And using back calculations, we identify what type of tissue has the X-ray passed. Observing tissue reactions to different energy sources provides complementary information about tissue types and aids in disease identification. Higher energy sources like X-rays or gamma rays can reveal molecular level information because their wavelength is comparable to the size of the molecules that they are revealing information about. Conversely, lower frequency sources like visible light or near infrared light reveal macro level information. The process of observing these measurements arising from different modalities is what we refer to as the forward problem. So the energy hits the tissues, and what we get are measurements, maybe in terms of voltages and so on. And this is called the forward problem or the direct problem. And typically from imaging modalities, what we want to understand is what did the energy source pass through, or the internal mechanics or internal composition of the tissues. And this problem is what is called as the inverse problem, from the measurements going to the tissue composition space. And when we want to observe a 3D volume, we need to have a source and a detector arrangement that covers this entire 3D volume. And as a result, we have such huge imaging systems, which you might have seen or possibly undergone a scan as well, having that provide non-invasive tomographic images of the patient's anatomy. So if you take the brain as an example, the same information or the same structure, tissue composition is giving rise to different kinds of information depending on the energy source we provide to that particular anatomy. So there is a lot of functional information in positron emission tomography scans, where it shows up depending on the radio tracer, most commonly used radio tracer is FDG, fluorodeoxyglucose. And this is an isotope of the regular glucose which runs in our body or the blood. And the high intensity, which is the red, shows up where these glucose molecules can get deposited. And if there is a unusual uptake of glucose, that could be indicative of some cancerous tissues. Similarly, MRI shows a lot of soft tissue information. You see this white matter, gray matter textures which are shown. However, it lacks the information to distinguish between bone as well as air, because it images protons. And air and bone both have limited number of protons that could be imaged. On the other hand, CT of the brain does not show anything inside of the brain, which has a lot of soft tissues like fat and proteins and so on, but it can clearly distinguish between bone and the brain. So the modeling of these systems involves writing of differential equations pertaining to the wave tissue interaction, what kind of wave was used to irradiate the anatomy, as well as how the tissue interacts with it. So it depends on the kind of source energy used. Subsequently, we can arrange them into a linear system of equations where A is characteristic of a particular imaging modality, and it captures the differential coefficient equations, you could say. X is the image to be reconstructed, and B is the set of measurements like voltages in detectors and so on. So the considerations to be made are: how was the measurement made? Is it really linear? What are the noise characteristics of the data? And what are the detector modules being used and what kind of noise can be captured in these modalities. For example, if we take the example of a CT, if we consider that our image to be reconstructed as a 3x3 grid, we will have the following measurements, M1, M2, and so on till M6. And we want to know the values of F1 to F9. That is the reconstruction problem that we are after. And our forward problem would look like this, where in CT, it depends on the angle at which you are passing the X-rays. So CT is a combination of X-rays at multiple angles, and then the 3D volume is reconstructed. So to generate M1, the rays pass through the diagonal of a particular pixel. So for example, if you take M1, it has not passed through any pixel, the coefficient is 0. For the second, in this pixel, it has passed through a √2, because if we assume 1 unit square on each side, the diagonal is √2, and so on. So you can arrange the length traversed by each of these rays in these pixel grids, and then you can formulate a linear system of equations like this, for which there are multiple solutions available or methods to solve these linear system of equations by obtaining a set of measurements around the body. Similarly, in MR, the forward problem happens to be a Fourier transform, and the equivalent in the CT is called the radon transform. So you can arrange these depending on the modalities and the kind of signal that you're generating. You could arrange these linear system of equations like AX equal to B form, where the system matrix differs across modalities, where in the case of MRI, it's in a Fourier transform, like I said. In the case of CT, it's a radon transform. And in the case of positron emission tomography, it's also a radon transform, but impacted by Poisson noise and so on. With the need for faster acquisitions and undersampled measurements, it becomes important to model the system more accurately. Else it becomes hard to recover the images. If we have all the time, then we can wait for good signal to noise ratio, and we can acquire good quality images. But we want to reduce the time spent by the patient in the scanner. So undersampling, can we obtain good quality images by undersampling the data that we need? Is something of interest for the medical imaging community. So for example, here the first row of the image shows squares with increasing photon count. So this is without any noise. All the pixels in a square have the same value. So in the second row, Poisson noise has been applied. And in the third row, Gaussian noise has been added, and as an approximation of the Poisson noise. The variance of this Gaussian noise can be adapted to the pixel values, using the relation. When you adjust the standard deviation of the Poisson and the mean, then you have adaptive Gaussian noise, which replicates the Poisson noise. So adapting this variance makes the Gaussian noise very close to the Poisson noise, except for the darkest squares. The fourth row shows the mistake that must be avoided, which is using Gaussian noise with a fixed variance. Then you start seeing intense noise patterns within the darker regions of this image, and this is analogous to our night vision, not night vision, camera with which can image even at a low light or night light. With very low photon count, your noise increases, and then modeling or recovering the images, recovering good quality images becomes very difficult. And we should also be careful that once the images have been reconstructed, if we are performing any image processing application in the signal domain versus the reconstructed image, we need to know the kind of noise characteristics that are there. For example, in MRI, the acquired image or the acquired measurements are in the K space or the Fourier space. So the noise here, the acquisition is on a CCD sensor. So complex Gaussian is the noise that is typically assumed or modeled for the measurement space, whereas the reconstructed image has what is called as a region distribution. So the probability distribution functions of both region and Gaussian are different. So if we assume Gaussian noise for the image, we would be introducing certain image artifacts that are not expected in the image space, and vice versa. So in general, in the general context of image processing, images consist of both texture and some cartoon component. Every image can be thought of a linear combination of a certain cartoon component and a certain texture component. So prior to deep learning era, you could say, for image processing, image gradient-based penalties versus patch-based penalties were used, which could exploit these features in an image. And you could, depending on the kind of image pattern or characteristics that you are after, you could adjust the image processing algorithm to achieve certain characteristic. For example, you have seen the CT image, which is more smooth and it just relies on sharp edge boundaries between the brain and the bone. So then priors or regularization techniques which enforce more cartoonish behavior might be preferred, whereas such techniques are not so useful for MRI, which is texture heavy and so on. So these are some of the example applications in medical imaging community, medical imaging computing as a whole. For example, in image reconstruction, you have undersampled reconstruction and parallel imaging, like we like we spoke about. There is image segmentation where there is at every pixel you want to know which class a particular tissue belongs to, so that becomes semantic segmentation. If there are multiple instances of tumor, you want to name and differentiate these instances, so that becomes instance segmentation and so on. In classification also, you want to grade the tumor or classify the disease and so on. You could also use image classification to assess the image quality, whether the image is good enough or good enough for an AI-based algorithm to run. So this could also be an application for image classification. So if you look back and see how the trends have evolved in both in image processing for supervised and non-supervised, or non-supervised includes both self and unsupervised learning, is that we know that UNet revolutionized the way we use our networks. It was introduced for segmentation, but the whole point of being able to break down, go to multiple resolutions of the image and being able to reconstruct the images using skip connections and so on, CNNs provided a very good architecture, which is used very, very widely. And then there were a lot of, then the introduction of GANs introduced allowed images to be augmented with synthetic images and so on. RNNs and LSTMs came in to address dynamic sequence images or videos that could be improved. And then came a very big paradigm shift in transformers, and more particularly vision transformers, where you could have non-local relationships between patches of images at one part of the image versus anywhere else in the image. So it was no longer localized to sequential patches, typically where CNNs operate, but non-local relationships were captured using these transformer architectures, which is quite robust in capturing the image statistics. Similarly or parallelly, in the case of self-supervised or unsupervised learning, we had deep image prior. The architecture is not important in deep image prior. They typically tend to use a unit, but in theory, any architecture could be used where the noisy image itself is used to denoise the image. And then came autoencoders, which could be learned, which could be used to learn certain features in the images, and by tweaking these features, you could give rise to synthetic images, or understand what features can be altered in an image to generate different kinds of images. Then even if you have unpaired set of data, that also comes under self-supervised or unsupervised learning, where even using GANs, you have a bunch of patients, let's say, with a particular contrast in MR, but a different set of patients with a different contrast in MR, and you want to learn and you want to complete the matrix of, given a contrast, you want to estimate how the other contrast will look for the first set and vice versa for the next set. Cycle GANs or bidirectional GANs were quite similar in that sense. Then came graph neural networks, meta learning, where the labels are not entirely present in our training set, but by iterative learning and having pseudo labels for certain applications, you could improve the already existing model. And then we have the latest models of diffusion models, where from noise, iteratively introducing certain restrictions on how we produce noise from a good image, that tends to learn a probability distribution of how to go from noise back to the restored image and so on. So if we look at particular examples of all these architectures that we have spoken about, and we consider the problem of image reconstruction in MRI, what is the actual problem is to reduce acquisition time. The signal sample needs to be at rates that are far below the Nyquist sampling rate. And to avoid artifacts resulting due to these subsampling, we need powerful denoisers or prior knowledge about the signal. So this is where CNNs have helped. They have further helped in accelerating MRI acquisitions by providing accurate reconstruction of heavily undersampled acquisitions, including much improved image quality. So they are also robust to changes in data acquisition. So you need not, because they participate in any typical optimization problem or a reconstruction problem, you have both data consistency term, that is the acquired signal is also participating along with the CNN denoiser. So it is not like we have to train the algorithm with just a particular noise level. It is robust to any sampling pattern as well as noise characteristic in the acquired case space. So using the same denoiser, we could address the reconstruction of practically multiple factors of acceleration. For example, this paper shows 6-fold, 8-fold, 10-fold, and so on. Very aggressive undersampling they have done and shown that the image quality is comparable across these acceleration factors. If we take the example of GANs for medical imaging, with the gaining popularity of GANs, more image to image translation, like the example I gave, you have contrast of one particular contrast, and you want to move to another contrast for better visibility of the tumors or structures. So a lot of image to image translation tasks were being published. This is one of my favorite papers in MICAI, and where it rightly warns about the perils of using data distribution matching losses, which is exactly what GANs do. So that is when using GANs, trying to predict a different data distribution from a given data distribution, the training set needs to be carefully chosen. So as you can see, this was a task. The author had tried to go from a flare contrast. This is flare MRI images, and from here to a T1 based contrast. So he has shown, so along the columns, you see the results of translation when 0% of diseased cases were used, 10% of diseased cases were used, and all the way till 100% of diseased cases were used. So as you can see, when you have a lot of diseased cases in the training set, so you have taught the network to only look at diseased patients, so it reconstructs the diseased tumor properly. Whereas in the training set, if there were no diseased cases at all, it virtually completely removes the tumor off, even though the flare or the input modality tends to show this tumor to a very large extent. So that is why this balance of the training set is very important, and image to image translation tasks need to be very carefully handled. There are some seminal series of self-supervised, if you see venues like ICML and TPAMI, which talk about restoring images even in the absence of ground truth. So this is one paper which started it all, I think. I might be wrong if there are papers before this, but this is a technique called blind denoising. This refers to the ability of denoising the images without needing any clean images. as references during training. So instead, the model learns to reduce the noise by relying solely on the noisy images themselves. So this leverages the redundancy present in the image data and the statistical structure of noise by masking the images and trying to predict the masked pixels from the unmasked one. So inherently, it is learning to predict the structure of the image, and noise gets eliminated in this process. Techniques of self-supervision have also been, so these self-supervision techniques that you see, they have also been recently extended into medical imaging, especially in areas where dynamic scans are required and the statistical property of images is exploited to improve the SNR. Like in the previous example where you saw certain pixels are masked, and that produces a lot of training data, and this masking can be random. You could generate multiple random masked versions of the input image and then try to predict the actual structure of the image. Similarly, in dynamic acquisitions, you could have multiple frames that are arising as a time series data, and then you could have even more powerful data when you consider patches of images, not just multiple frames stacked against each other, but patches of images stacked against each other. So that gives rise to a huge regression matrix. And then you could predict just a center voxel. In this paper shows that all these measurements that you're making, it just predicts one voxel at a time. And then you have the entire denoised image, and you iterate through this process for multiple frames in the images. Now, I'll move on to some examples of image processing techniques, AI-based image processing techniques, which we use at Philips. Any questions till now? Hello?
Yes, sir.
Any questions till now, or should I proceed?
Sir, you can proceed, sir. No.
Okay, thank you. Okay. So this is the first application. I'll talk about two applications. This is called smart planning for cardiac MRI. So the problem is that we want to improve and improve the precision and efficiency in cardiovascular imaging. That is what the what the actual problem is, that given a low resolution image, that is a preparatory phase image, when the patient enters the cardiac exam, as you might know, cardiac exam takes a lot of time. Typically, it's 45 minutes long for a patient. And you cannot acquire the entire heart at the rate at which is beating. The MRI image of the heart cannot be acquired given the rate at which it is beating. So what typically technicians do, or MRI operators do, is they decide on certain 2D views resulting from these 3D arrays. So let's focus on one view. For example, the 4-chamber view, where you could see all the 4 chambers of the heart. Given this 3D image, a slice is made, a cut is made in the console, uh, in the MRI console. A 3D cut is made for the surface, and you could arrive at such an image which focuses only on the 4 chambers of the image. So if you cut anywhere in an orthogonal direction, left to right, head to foot, and anterior posterior, you might not receive this kind of an image because the heart is tilted that too in a 3D space. So you need an oblique plane that cuts across the heart to have such a view. So we use deep learning. So there are not just one views. There is not just one view. There are multiple views like this, and typically 8 to 9 views are used. We have just shown 4 most important views over here. And then once these 2D views are made, the image acquisition is only along those 2D axes. So imaging one 2D image across time becomes easier in MRI, especially in MRI where the acquisition time is quite high compared to CT. So there are multiple oblique planes that are drawn by the operator, and then the acquisition actually starts. So this preparation itself takes about 10 minutes, not to mention that the person or the operator needs to be a cardiac expert to know where exactly to cut this 3D volume so that these kind of images can be captured, where the 4-chamber view is supposed to show the 4 chambers. The short axis shows the myocardial valve. The left 2-chamber and right 2-chamber look like this, and there are certain views where the aorta is visible and so on. So each view has a specific purpose where you could assess the function of the heart. So just to formally state it, the conventional cardiac MRI workflow involves the acquisition of multiple double oblique views like we discussed. And this is highly operator dependent. So the same operator, if he does the planning the second time, that could be slightly different. And it could vary from operator to operator as well. So it is highly operator dependent and time consuming. So this complex planning, in addition to variation in the heart size, for some heart disease conditions, the heart could be really large and then it becomes really challenging to plan. And the position of the patient, the diaphragm might be constricting the heart movement, and then the heart might be lying horizontally on top of the diaphragm and so on. So this both variation in the heart size and the position of the patient necessitates cardiac MRI expertise for such scans. So thus, what we see is cardiac MRI is performed only in very few diagnostic centers. Not all diagnostic centers which have an MRI can perform an cardiac scan. So if we were to enable automated view planning, this would reduce, first of all, the variability in the planned views. So the same image or a same patient would result in the similar views uh, across time, and also across operators or across operating centers, you would have a similar planned views for a given input, right? So this reduces both inter and intra technician variability, and also it can potentially enable cardiac MR scans to be performed at multiple centers where even entry level operators are trying to take MRI scans, and they could also plan cardiac MR scans. So there are standards how these different imaging planes are realized. Commonly used are the ones we saw: short axis view, 4-chamber view, 2 chambers on the left and right, and so on. So there are standards that are made. You take the 3D image, you make the cut along a specific axis, you arrive at the vertical long axis, horizontal long axis, and so on. And what is more challenging is once you arrive at the penultimate plane, you have to check from reference views whether all the other features are visible and all other planes are behaving with respect to each other. That is, whether they are orthogonal and so on. So this becomes quite challenging if one of the views are in the entire process has gone wrong, and then the process has to be started from the beginning again. So it's quite challenging to obtain these things. So we thought, how could we do this with deep learning or machine learning for that matter? So we employed two approaches. One where for each plane, because each plane could be represented by points in 3D space. So each plane was given or annotated with at least 3 landmarks. And then for about 10 planes, we had close to 40 landmarks. At least 30 landmarks were required. We ended up annotating about close to 40 landmarks. And then what we solved is the input to the we used a unit-based model where the input is the 3D low resolution survey image. Survey image is the low resolution image, and the output of the network, what the network will output, is the coordinates of these landmarks, and these are obtained as a heat map regression function. So so it would contain a tuple of 40 landmarks, each giving the XYZ coordinates of the landmarks which are already annotated. So it learns to predict the annotated landmarks from the training set, and given a test image, it would predict these landmarks in the 3D image. So the loss function we used was mean squared error between the predicted and the ground truth coordinates. And once the set of landmarks are obtained, that is these 40 landmarks are obtained, we fit a plane across the corresponding points. So for example, we know which of these three, they are ordered in a specific way. So we know which of these landmarks correspond to a particular plane, let's say the 4-chamber plane, and then using singular value decomposition or principal component analysis, we can draw a plane through these points. This is the conventional approach which is present in the literature. And then one of our team members, they came up with this idea that what if we solve this problem as a semantic segmentation problem? So these are the planes that we have. Once it is annotated, this is how they would look. And we slightly modified the problem. Instead of solving it as a regression problem, we started solving it as a semantic segmentation problem, where the masks or the planes participate like masks, or what is given to the network to learn a segmentation is the mask, where these lines that you see are actually planes in 3D space. So the mapping is learned between the input 3D image, and to generate these kind of slabs, or because it is given a slight thickness, you could consider them as slabs in 3D space. So they have a finite thickness, and then it learns, then if you see this mask image that comes out, it's intuitive that it is trying to learn the relative positions between multiple planes that exist in this 3D space. So the relationship between the 4-chamber view or a 2-chamber view, the vertical long axis and the horizontal long axis, all these relationships are preserved, and that is what the network learns. So we used a unit model again, but this time to solve a segmentation problem, semantic segmentation problem, where at every pixel, the value assigned is which plane it belongs to. If it belongs to the background, of course, it's 0. And if it belongs to a particular plane, that particular plane number is given. So we had 11 planes to predict. We gave the numbers 1 to 11 for it to be predicted. And these are the mask images that you see. And the results improved dramatically compared to the regression problem that we were solving. So here, of course, because it's a segmentation problem, the loss function was modified to have a multi-label dice score, iterating across multiple labels that we have, and as well as a pixel-wise cross entropy. We also used the same data augmentation that we used for the landmark-based approach also. That is, we added noise to the input. We created anisotropy, voxel distortion, and so on. We rotated the images. We involved dropout. We performed 5-fold cross-validation and so on. So to improve the inference time as well as the performance, we even cropped the image. We identified the heart, localized the image so that we can crop and focus, so that the network focuses only on the region of the image, not the entire image. So the plane prediction accuracy is much improved because it has to draw these planes only in these regions of the heart, not outside. And once we obtain these masks, it is not the actual plane, because if you see the prediction, they could be considered like a cloud point, which is just present in 3D space. But you have, for example, for a particular view, it could be a cloud point which is spread across this thickness of the slab. So there could be a lot of outliers as well. And then you could use these cloud points to then compute the views in the same way we used in the landmark-based approach also. That is, now you have a lot of landmarks, multiple folds of landmarks to predict one particular plane. Earlier, you would have only 3 or 4 landmarks, but you could use some technique like ransack, which is a nice known technique to fit a plane through a cloud point. So once these cloud points are obtained in 3D space, then the plane could be drawn using ordinary least squares or principal component analysis or ransack, any of these methods to finally arrive at these planes. So what we observed was not only did the accuracy of planes that were being predicted improved, but it could even handle slight degradations in the image quality. So it was robust to that level. So that is why we believe that the spatial conformation of these planes is well learned by this model compared to a landmark model where slight perturbance, because there are only 3 points, slight errors in one of the landmarks could result in uh, enlarged error or exaggerated error in the plane prediction using the landmark-based approach. So these are just comparisons of the landmark-based approach versus the plane-based approach. So the red line is the ground truth or the truly annotated plane for a given test subject. And we see we are also slightly off in this particular tough to estimate view, but the landmark model suffers even more. And these are viewed from reference planes. So you would see in the 4-chamber view as reference. 4-chamber view is reference for the left 2-chamber plane that is acquired, and the at least from one of the reference planes is quite close to the ground truth compared to landmark, which has completely tilted the axis, and then it becomes difficult to assess which plane are you looking at. We'll move to the next application. This is MR computed attenuation, that is estimating CT-like images from MR-like images. So traditional radiation therapy workflow looks like this, where MR and CT images both are acquired separately. And then, so MR can show cancerous tissues or the tumors and the surrounding organs and the soft tissues quite well, whereas CT can show the just the distinction between bone and non-bone tissues. So both are required to actually pass the energy, high energy beams, which can actually treat the cancer using high energy photons. You need to perform some treatment planning, which can be provided by CT-like images. So once you know that the energy is attenuating, in case of CT, it is the X-rays. So if the X-rays are attenuating so much within these structures, you could extrapolate and know how much will a proton beam attenuate. So that helps in planning these radiation therapy procedures in the linear accelerators. But on the other hand, MR gives you the information of where exactly to localize these tumors and plan the treatment in a way that it does not affect the surrounding organs. So if the tumor is present in the brain, you don't want to touch the optic nerves and very sensitive structures like the hippocampus or the corpus callosum, which can be very sensitive. If the radiation is deposited in these structures, the brain is damaged to a much larger extent, and the function of the being also comes down. So once the MR image is acquired and the CT image is acquired separately, there needs to be an image registration procedure between these two. And then based on the registration of these two images, you need to contour the target, that is the cancer, as well as the surrounding organs at risk. And then the dose is planned as to how these high energy photons are going to enter the body in such a way that the tumor or the energy deposition at the cancerous tissue is maximized while minimizing the damage to surrounding organs at risk. So this is not just done once, it is done across multiple times. So there are 5 to 6 settings of radiation therapy delivery. And then there is follow-up where the tumor size is going on reducing. So every time you have to do the MR and the CT and then the registration and so on. So what we provide as a solution is a MR only the radiotherapy workflow, where in the original case, you had to acquire a CT, you had to do an MR, then register, and then do the delineation of the target as well as the organs at risk. We create a CT-like image from the MR image itself, and then we eliminate this additional step of CT image acquisition as well as this registration process. The registration also has a risk because the patient might have moved, the patient position might be slightly different in MR and CT. So registration is quite challenging given the systems are different. It could even happen the subsequent days. It might need not happen in the same day. So that way registration is quite challenging. So at present we have 4 different products in the market where given MR images of these anatomies, we have corresponding CT-like images. So we have pseudo CT or MR-CAT images of the pelvis, prostate, brain, as well as head and neck. Head and neck is a longer acquisition of both brain plus the neck area where more tumors could be seen. And currently the brain and the head and neck are both AI-based, deep learning-based regression problems where input is a combination of multiple contrasts from MRI that come in, and the predicted images are these CT images, CT-like images. So if we take the specific example of MRCAT brain, we use the M-Dixon contrast. That's a T1 weighted scan. We use both in-phase and water images. These are the 2 contrasts of MRI that are used as input to the network. You produce the MRCAT, and finally the dose is planned based on the MRCAT. And this MRCAT is used to position. You generate a digitally reconstructed radiograph or an X-ray like image, which is used to place in the linear accelerator for treatment purpose. So these are what the images look like. These are 2 different contrasts from the same subject. These images are obtained from a sequence that is called as M-Dixon. And then this is the corresponding CT of the patient. We have a set of all these images which are used for training. So the patient underwent both MRI and CT scans. We registered them. We created such a set, and using supervised learning and unit architecture, we try to predict, given an MRI image, what does the CT image look like. So the input is water and phase, like I said. We also produce a foreground background mask to enhance the signal, and then we do a 2.5D based regression approach where for a one slice, 2.5D is an approach where to predict one slice, it's a 2D output, but as an input, you give 3 slices at a time so that the 3D context is learned. So 3 slices at a time coming from multiple modalities. So it's a 9-channel input altogether to the model training, and 1 slice is predicted at the end. And you iterate over multiple slices, then you get the entire 3D volume reconstructed. So that brings to the end of my presentation. A few takeaways that I want to just call out is that because medical image computing is a slightly sensitive area, we need to understand the origin of data and the exact measurement model from where these signals are arising. The domain could be different. Variation in acquisition strategies can give different measurements. The noise characteristics could be different, and so on. If we are going from one data distribution to other data distribution, like you saw in the case of MRI to CT, you have to be careful about the data distribution. That is, are you giving the right mix of diseased and non-diseased patients? Is it covering the entire, or basically to avoid memorization of the network, and visualize the data, right? Most of them, if we have this advantage in image processing to visualize the intermediate steps and make alterations to our modeling or solution that we are in the process of making. And then meaningful pre-processing techniques, whether the imaging modality that we are handling is a quantitative versus a non-quantitative data. Then, for example, histogram equalization techniques are probably a bad idea as far as CT is concerned, because it distributes the intensities. I mean, the process of histogram equalization is to enhance certain areas of the image which appear darker, but this might completely spoil the data in case of images like CT, where each pixel actually means a physical value. and design the model and the loss functions based on what evaluation metrics we have. So in the case of the cardiac planning, we saw that by slightly altering our thought process and modeling it as a segmentation problem, we could achieve much better accuracy. So modeling it as a segmentation problem involved modeling the loss function as dice and cross entropy and so on, and then that improved the accuracy a lot. And what are some of the important problems to consider? For example, when we go from one distribution to another, we need to say that one thing where information is lacking is if we are not producing the right output, can we quantify somehow that I'm not sure about the output that I'm creating? So uncertainty quantification is one active area of research, and it has to be real time, whereas current uncertainty quantification methods are quite time consuming, and in real time in clinics, these are not adaptable. And then things like anomaly detection, when you see something wrong with the image, it could be a pathology or it could be image quality based issues where you inform to the operator that there is something wrong with this image, either with respect to the image quality or the pathology, and then additional scans can be planned rather than after the patient has gone home and calling him back for another set of scans. That is not ideal. And root cause analysis for failures by visualizing the model and trying to understand why exactly a test data is failing or failing to produce a required output or a required kind of output. One more, this is the last slide. I just want to uh, point out certain venues which we can keep looking at to improve or contribute to the community of medical image computing research in general. We can do so by participating in open challenges where benchmarks are already provided. So if you look at websites like grandchallenge.org, it has multiple challenges for multiple image computing problems, classification, segmentation, reconstruction, and so on, even registration. So there are data sets and the rules for participating these, and you could also make the code public so that the community benefits from it, and we only keep moving forward. Otherwise, there are challenges from conferences as well, which come once in a year only, but these are also specific challenges coming from different research universities. And we often talk about lack of data, lack of annotation, and so on. There are large open source models available, such as Total Segmenter. If you give any part of the anatomy from a CT or MR, the segmentation of these anatomic regions are visible. There are libraries like medical segment anything where it's a prompt based segmentation. You can place your cursor in a certain tissue type and it can try to segment on its own. So it has been trained on, it's a foundational model where it has been trained on multiple contrasts, multiple any imaging modality for that matter. And when we lack data, we could also use libraries like Torch.io, which are used for data augmentation and so on. And one recommendation would be to use harmonized frameworks. For example, NVIDIA comes up with a harmonized framework for right from data annotation, training, as well as deployment and inference. So these are called, this is the Monai architecture, where it provides interface with open source image viewers where annotations of data could be created. So it is called Monai Label. There is a training platform, data loaders, and pre-processing techniques are already built in and provided as open source. That's called Monai Core. And finally, Monai Deploy, where you could convert your models to easily loadable formats. And an inference framework is generated where multiple inferences could be run from different models. Maybe for the same image, multiple AI models need to run. And then you could think of arranging these AI models in a certain scheduled manner, the framework for which is provided by Monai Deploy. Yeah, that's it from my side. If there are any questions, I'm happy to take.
Dear participants, so this is the end of the session by Dr. Viswanath PS, scientist, Philips India Limited. If you have any queries, so it is open. So he has given a more information how actually the MR and the CT has taken. So he gave the information so totally. So what are the basic, what happens when access changes and all the information is given. So if you have any queries, please. Sir, many of the faculties.
Your voice is quite feeble. Could you please increase your volume? Or I'm at maximum volume.
So now it is audible?
Yes, now it is much better.
Yeah, faculties, if you have any queries. Yeah, it was a wonderful session, and it helped our faculties. So those who are on the research background of MR, so medical imaging techniques. So how actually the imaging takes place, which axis is better. So when we take the MRI, CT in the multiple axis, so it is if it is a manual, of course, it will differ from one type. So first time to second time or a third time scanning. So when it comes to the new technologies, of course, the errors are very minimum. And whatever the data set you've shown, it is a really wonderful, sir. Dr. Siddesh, HOD, Department of ECE, so will thank us.
Hello. Good morning, Krishna sir. Hello. So you have given a wonderful input to our participants, research scholars, and you have given how we have taken especially in the field of medical imaging research, how to compute those things, those data sets we have taken from the respective fields in MRI, some scanning areas. So how to compute all those things. You have given wonderful ideas for further research. And I thank you for all giving a lot of inputs to our participants. Thank you, one and all.
Thank you, sir. And the feedback link has been shared. And afternoon session will be at 3 o'clock by Dr. Leena Chandrasekhar, Professor, ENC Department, RNSIT, Bengaluru. So the link will be shared at 2:30 p.m. and the session will start at exactly 3 p.m. today afternoon. Thank you. Thank you, sir.
ಅಬ್ಬಬ್ಬಬ್ಬಬ್ಬ ಇವತ್ತು ಎಂತ ಲಕ್ ನನಗೆ ಅಂತಂದ್ರೆ ಆನ್ ಮಾಡಿದ ತಕ್ಷಣ
ಒಬ್ಬರೇ ಎಲ್ಲರೂ ಮಾಡಿದ್ರೆ ಮಿಸ್ಟೇಕ್ ಆಗೋ ಪ್ರಾಬ್ಲಮ್